Have you ever wondered how expensive it is to put a satellite in space that can actually do something? Well, ipXchange chatted to Brown Space Engineering, who did exactly that on a budget of around $2,000. So where did they have to cut the costs? Hello, ipXchange community. We're here with another project, this time with a lot of people, which is not what we usually do, but we couldn't do this without all of them. So I'd like to introduce the Brown Space Engineering Club, and we'll just do a roll call of what each of them does in the in this project, which is to do with 3U CubeSats. So Dan, would you like to start? Just say a little brief thing about your role in the club and how long you've been there.
Yeah, totally. So I'm a recent graduate at Brown University. This past year, I was the project manager of the club, co-project manager with JB here, who is going to succeed me. I was also on the structures team where we worked on all the structures on the satellite, from the chassis to the arm to all of the release mechanisms. As I am a recent graduate, I'm going to let the current students take the spotlight. I'm here as a resource if anything from the past comes up. But yeah, I've been in the club all 4 years, and I'm super excited to be here today to talk about this.
Cool, nice. And I think that's a perfect segue into JB. What do you do in the club?
Hi guys, I'm JB. I am a junior at Brown University. I am the current project manager or president of the club. I came into the club about 2 years ago. I started out in structures, but most of my work back then was actually focused on what we now call ADCS, which has recently become a new subgroup. And would love to talk more about all of that.
Cool. And Milan?
Sorry, my mic wasn't working for a second. Hi, everybody. My name is Milan Kapoor. I'm a junior at Brown University. It's my third year at Brown Space Engineering, and I am one of the co-leads of the Attitude, Determination, and Control Systems team that JB just mentioned.
Nice. And Colden?
Hi, yes, my name is Colden Bobwick. I'm going to be a senior at Brown University. I've been with the club this will be my 4th year. And I'm also Attitude, Determination, and Control Systems co-lead with Milan.
Nice. And Siddhartha?
Hi, I'm the current treasurer of Brown Space Engineering. I joined about 2 years ago. I started off working in flight software and still am under, there's a subgroup that Danish is now leading. That's pretty much it. I'm working right now on testing effectively the correctness of the algorithms we have on the satellite and the budget.
Cool, nice. And that is a very important point that we will be talking about. And last but not least, Tanish, what do you do in the club? And after that, can you give a little bit of history of Brown Space Engineering and how long it's been going?
Yeah, so I'm Tanish. I'm a rising junior in Brown Space Engineering. And I started out just my freshman year as a normal flight software member, but next year I'm going to be the incoming flight software lead, so that'll be a lot of fun. That's about it for me. I think if JB or Dan wants to give the history.
Yeah, sure. So Brown Space Engineering was founded in 2011 with its first mission called ipXchange. That was a 1-unit CubeSat designed as a proof of concept for inexpensive satellite and as a first ever space test for lithium iron phosphate batteries. It notably had really large flashlights and was visible at night with naked eye. So that was really cool. It took us about 10 years to build, design, and test the whole thing, but we gained a lot of experience. After that, there was a brief side project called Sputnik, in which some BSC members participated. That was a 3-unit CubeSat with a new thermal dissipation system and deorbiting mechanism. And that brings us to PVDS. As you can see, we have 6 subgroups, 5 of which are responsible for different aspects of the satellite. There's also R&D, which works on shorter-term projects like stratospheric air balloons and plant experiments. And the subgroup leads have introduced themselves. There are also a few that are not currently here.
Nice. So I guess probably the best thing to do is now is to go into this new 3U CubeSat. So can you describe some of the main components of this, and then just afterwards, how are you going to be placing it in orbit?
Yeah, sure. I can start with some of the brief overviews. So the full name of PVDS is the Perovskite Visuals and Degradation Experiment. It is a 3-unit CubeSat with 2 missions in mind. So one, it tests the performance of experimental solar cells made with perovskite minerals in space. And if successful, those solar cells may provide us with a more efficient form of solar power. And secondly, it acts as an educational platform for K-12 students from all over the world. There is a programmable screen on board that can show the output of students' coding projects. And the primary feature is a deployable arm with a camera attached to it that allows us to visually monitor the solar cells for degradation and the screen for output. And anyone feel free to jump in with more details with your respective technical parts.
I mean,
I can talk to the structures team. I think that's a great place to start. I'll make it quick and brief. Basically, structures deals with all the physical hardware on the satellite. So as I mentioned before, the chassis to deployable mechanisms like our arm, which holds the camera. The chassis is basically the main metal structure. This is the heart of the satellite. This holds everything together, right? From the solar panels to all the internal components, the batteries. This is kind of the main hub that everything mounts to. And kind of all the other components are designed around that. And then I can also talk to the deployable mechanisms on board. So we have a deployable arm, which holds a camera. When the satellite's launched, it can't have any parts outside of the frame. So everything has to be kind of tied together when it goes into the launching unit, and then up into the rocket and into space. So we had to come up with a way to tie this thing down and then be able to talk to it in space and then have it launch in space. So the camera ends up on the outside of the satellite so we can view the outside panels to conduct the experiment with the perovskite solar cells and also view the screen for the students to communicate with. So that's the structures team. I can pass it off to ADCS if that works.
Yeah, I'm happy to explain attitude determination and control systems team. Basically, once we're in space, 30 minutes after launch, we power on and we are tumbling in some unknown orientation. So our job as attitude determination and control systems team is to first detumble the satellite so that we have relatively zero angular velocities, and then design some algorithm that points the satellite at Earth so that we can use our S-band communication systems. Since they're single directional, we need to be pointing within a 15-degree radius at Earth for the communication to work. So that's our job, is making sure that we can point at our ground station so that we can have quick uplink and downlink to the satellite.
Cool. And I'd just like to ask, what orbit would this be in as well?
This is going in relatively the ISS orbit. So it will be launched out, I think, through a CubeSat cannon, sort of, off of the ISS.
Well, 1 to 2 years, barring any sort of anomalies or just things breaking down.
That might be a good segue into kind of what flight software is doing. So our job is to enable all of these peripheral devices to actually communicate to each other through like a central operating system. So in total, the satellite's going to have the deployable arm in the beginning. On the arm is a camera that can take pictures. Its field of view is mostly covered by the satellite itself. So it'll be kind of looking down at itself with hopefully a very small bit of the Earth in the background. And on the side of the satellite that it's looking on, we'll have those perovskite cells that we're testing. Hopefully there will be some way to measure other aspects of the perovskite cells. We also need to control, of course, like the battery, measure the thermal readings from the battery, and attitude control needs to run through flight software's code as well. So there's a Oh, and I was forgetting. There's a display as well. So
Oh
part
yeah.
of a secondary mission alongside these perovskite cells is kind of educational. We want to create we have a whole other software team, ground software, um, that's working on creating some kind of interface to help students learn how to code. And the idea is that once they reach certain checkpoints along their journey, they can send it up to our satellite and have some neat little thing display on it, and then take a picture of it and send it back down as like kind of,
Sweet.
that's like a really cool, like, I don't know, if I was learning how to code, I feel like I would be pretty hyped if that happened. So
I mean, it's a similar concept to things like Scratch, except we're sending the picture up into space instead of keeping it on your screen. And so, of course,
Nice.
that implies that we need to receive from Earth a sort of tape. We need to receive the data of the finalized out picture from Earth in space, and then we also need to receive sort of the take a picture instruction. Similarly, we do need to beam down. We do need to beam down the picture that's taken back to Earth, both for the educational things and for the material sciences lab we're working with to see the degradation of the perovskite solar cells. Another important thing is every once in a while, the ADCS calculations do rely upon knowing a time difference, sort of timing each orbit. So we will have to beam up an updated time, with reasonable frequency if we want to keep the accuracy of our orientation. I mean, and there's also generally supposed to be a sort of console type thing that you can sort of type on. You can effectively type into a console on Earth and have a certain sets of instructions beamed up to the computer, to the satellite in space, and then depending on that, the satellite will send down some sort of output or warning message if something has gone wrong. And ideally, if something goes wrong at any point in orbit, there will be warning messages cached and sent back down to Earth when we pass over the communications hospitals.
Cool. So this is something that I was talking to Tanish and JB on the prep call, but something that I thought would be really interesting to describe is how this satellite actually physically orients itself in space. So I guess, do I leave that to Colton and Milan?
Yeah, I can start talking about that. So the problem of orienting physically in space is everything that our team at ADCS does. And because of our specific mission parameters, that's saying we need to have this camera receive data from the S-band and transmit from the S-band, and the S-band constraints give us the 15-degree code of accuracy that Colton mentioned. That means that more than most other CubeSat missions of our type and our size, we need to have pretty strong control over our orientation. So like the ipXchange mission that JB mentioned had no active attitude control because the important thing was not that kind of directional antenna, but just the fact that we could see the light and test the thermal qualities using our UHF radios, which are omnidirectional. So that gives us a pretty, certainly not unique, but an almost unusual position to be in for a student CubeSat because we need such strict attitude control measures. The problem about attitude control, now that we know that we need it, falls into kind of two categories, the determination and the control. The determination is figuring out where we are, how are we oriented, where do we need to rotate, and the control part is how do we actually rotate to where we need to be. And so figuring out those two problems, which work almost completely independently of each other, has been what we've been doing over the last year or so. I can talk a bit about our determination algorithm, and then Colton, if you want to jump in and talk about our actuators. But so determination is the first step of what we've done after we figure out the detumbling, which Colton mentioned earlier. And there are multiple ways to do detumbling for CubeSats of our size. One of the most common determination algorithms involves a sun sensor, which just figures out a vector towards the sun, and that is able to give us pretty constant accuracy just because of the difference and distance in between our orbit and the sun. It's almost a 6 point for us. It gives us a very good reference. But the problem with that is that just like on Earth, when you're holding a compass and that one measurement gives you total knowledge of your orientation in 2 dimensions, for 3 dimensions, we need at least 2 measurements. So what we've chosen to use is a magnetometer, which is kind of the analog of a 3-dimensional compass and gives us a reading of the Earth's magnetic field lines. that will always point us towards south. And having those two measurements together gives us total knowledge of our attitude. So that's what most people do. However,
Cool.
sun sensors are incredibly expensive for a project like us because you need 6 coarse sun sensors, which allow you to figure out which face of the satellite is facing towards the sun, and at least 1 or 2 fine sun sensors to get within the 7 to 15 degree accuracy we need. Coarse sun sensors are roughly $3,000 to $5,000 each. Fine sun sensors are on the order of $10,000 to $20,000. So for a student CubeSat where our entire mission up to now has cost us about $2,000, that's completely unfeasible.
Yeah.
There are ways to simulate the coarse sun sensors using our solar panel, but that still doesn't resolve the problem of the fine sun sensors, which would add tens of thousands of dollars to our budget. And so being a club that focuses so much on space accessibility, our mission statement is making space accessible. We found that completely intolerable and unfeasible. And so we have been, over the past year, searching for new ways and alternative ways to cut down on this cost and come up with a new, cheaper, more accessible, more reasonable method of attitude determination. So what we have settled on, and that we're still in active research for, is a magnetometer-only attitude determination system, and then simulating a second sensor to get us those 2 measurements we need. So that would cut down the cost from at least $60,000 to only a few $100s, which would be enormous for space accessibility and the potential for other groups to replicate our work, because everything we do is open source, documented, and our goal is for anybody to be able to come in and repeat it. And saying you need the resources of Brown University and $60,000 just didn't feel good to our mission statement.
Yeah, that's fair.
But so this is a huge challenge for us because, to our knowledge, we will be the first people to ever test a magnetometer-only determination algorithm in space. There have been some papers theorizing about it, but we'll be the first ones to actually implement it and test it. And so along with everything else we're doing, it's kind of unceded ground that's really exciting for our accessibility considerations.
Yeah, that's really incredible because I mean, you're obviously. Wait, is that 100-fold decrease in price almost?
Something like that.
Whoa.
Milan, you talked about how you determine the orientation after tumbling. So, Colden, did you want to say how it reorients itself and the mechanism behind that?
Yeah, absolutely. So there are a few ways to do this physically. One common approach is reaction wheels, which store angular momentum. And then by speeding up or slowing them down, we can alter the angular momentum of the satellite itself. Another good option is a gravity gradient, which effectively extends a boom far out from the satellite, and the difference in the strength of gravity from one mass to the other mass pulls it in a vertical orientation, which is a form of passive attitude control. And what we settled on, due to its simplicity and low cost and our ability to manufacture, is magnetorquers, which are a solenoid, a wrapped copper wire wrapped around a ferromagnetic core, which, when a current is induced in it, it produces a magnetic field, which tends to align with Earth's magnetic field. So by utilizing 3 orthogonal magnetorquers, we are able to create a magnetic dipole in any direction, which will allow us to effectively point the satellite in any direction that we.
Cool. So I guess that's a no moving parts approach as opposed to the okay.
And interestingly enough, on the Hubble telescope, I know a few of the reaction wheels have actually failed, which they have an unlimited budget, billions and billions of dollars, and the first thing to fail is still the reaction wheels. So we wanted something that had very few points of failure. Additionally, we wanted something that was simple to manufacture because that reduces our costs, and a low power option as well.
So just wondering on the low power part is because obviously any kind of solenoid or something, I understand there is a magnetic core in there as well, but how much current do those require to orient themselves in space?
So it all depends on the constraints, for each individual project, but we're using a very thin wire with a maximum amperage of, I believe, 0.1 amps. So we're staying below at 3.3 volts. So.
Okay, yeah, that's not too bad. Cool. So, Milan obviously kind of show that there are some serious budget constraints in a student project, even though you've managed to find some really, really innovative ways of getting round the $60,000 buy-in to having a satellite. So I think it'd be very interesting to approach what's some of the challenges that you guys have faced building such a complex project as a student without the kind of infinite budget.
I know on the flight software side, we're also dealing with very similar things because it's very standard to have radiation hardened memory whenever you're sending something into space. By radiation hardened, I mean coated with some kind of material or housed in a way that cosmic rays can't actually flip the bits in the memory as it's operating. But these also tend to be very expensive, on the order of thousands of dollars. And that's just not something we can really afford. I mean, our whole budget, like Milan said, up to this point has been around like less than $5,000. So we would really not like to add another few thousand just for a chip. So some workarounds that we've been experimenting with and we're in progress implementing are triplication of memory. So storing every piece of useful information 3 times, and anytime we want to retrieve or update that information, we do it at all 3 locations. And it's kind of like a majority rule. So if a cosmic ray were to come down and corrupt a piece of memory, the hope is that it will only corrupt one of those 3 locations. It would be extremely improbable for 2 of the 3 to be corrupted in the exact same place. And so the idea is anytime we do a read or a write, we check across all 3, and if we notice a discrepancy, we overwrite the 3rd with the majority of the 2. And hopefully that way, if we keep doing that, we can maintain the initial, we can prevent the data from going corrupt. And even if everything starts getting corrupted, we've also programmed something called a watchdog system. And it's basically a dedicated task that monitors every other task on the operating system. So at regular intervals, which we've programmed, it's different for each task. So for example, the camera might need a longer time than the display to do certain things. But each main task on the OS has a certain check-in time. And without fail, it must tell the watchdog, like, hey, I'm running okay, nothing is wrong. And if it fails to check in, then the watchdog will kick the entire system and reboot it from a known state. And so the idea is that with the triplication and the watchdog, we can avoid the costs of buying radiation-hardened memory. And of course, it's not ideal, but in theory, hopefully it will work.
Cool. And just for our audience's kind of interest, what operating system are you running, and on what type of device?
Yeah, for sure. So our main processor is an Atmel SAMD 51 P20A.
Cool.
And the operating system we're using is FreeRTOS. So it's an open source real-time operating system that we've kind of forked and we're modifying to our needs. And because we're using a chip from Atmel, they provide a software framework called the Atmel Software Framework, or ASF for short. And there's a lot of useful functions there for, I'm not sure how familiar with programming the audience might be, but with if you want to create like a queue or some kind of list structure with many items in it, then there's predefined functions that Atmel has provided to that these functions have been tested, and so they're much more likely to succeed and not be buggy than code we might have written from scratch.
Nice. And obviously that's very important when it goes up.
Yeah, I mean, obviously, like we're writing most of it from scratch, but just
Yeah.
as a starting point, having the Atmel software framework and FreeRTOS is very nice as a base point.
And actually, just out of interest as well, is do you have the option of firmware writing, like I want to say over the air updates, but it kind of doesn't feel right with space. Is that an option, or is it pretty much you set the firmware before it goes up and then that's it, and you're just it's just data and control signal that you can send?
No, unfortunately, that isn't an option because, well, I mean, the main thing is we don't have, because the operating system is stored on a specific type of memory which requires a lot of energy to write to. It's
Fair.
And so the thing is, just running off the satellite solar cells, running off the batteries, we will not have enough power to be able to write to the operating system section of the. We can't rewrite the operating system.
Nice. Okay, that's a good thing to clarify.
So it's sort of because of that, we need to make sure that we test everything quite extensively. And actually, you'd think that the bit flip thing would be quite hard to test, because it would sort of require putting the whole satellite in some sort of cage that would simulate the that would simulate the conditions of space. But it's actually quite surprisingly easy to test. It's a task that we actually give to people just entering the group, is that you can write a piece of code that will simulate the bit flips by just picking a random location of memory and flipping it.
Okay, cool.
So the thing is, the point I'm trying to make is that a lot of these things are actually, at least on the flight software side, are actually a lot easier than you might think.
Cool. So obviously there's various levels of experience and longevity in the club here. So I'm not sure who you'd want to nominate this, but what advice would you give to other engineers working on similar projects? And are there any like big mistakes or wins that you'd want to highlight for their benefit?
Yeah, sure. I can get that started on something in the project management side. I would say for a project as complex and long-term as building a satellite, having a very clear system of communication and accountability can be immensely helpful. And in fact, it's indispensable, especially as the team gets bigger. We have weekly logistics meetings with all the leaders. We have all of our notes, all of our purchase requests, all of our project timelines and task validations, all in Notion. That is not a sponsorship. That's just something we use. And that allows us to see what each leader is expected to do, and allows the leaders to see what each member is expected to do at any given time. I would also say, like, really early on, invest in a system of documents or files or whatnot that preserves institutional memory, because that has been a very crucial issue for us, because we have leadership turnover as people graduate, and we also have COVID, which really dampened our productivity for about 1 or 2 years. And now, as we're coming back, trying to finish the project, a lot of the times we have to reinvent the wheel, especially on the software side, because the previous code was just not available or lacking documentation for us to understand it. So I would say, like, having that system set up early on is going to be very, very useful later on.
Cool. Did anyone else want to say anything?
I can add on to that if you'd like. I mean, and genuinely, when you're dealing with projects this complex, money actually is quite a bit of an issue, because especially because we're doing a lot of research and development, so that means that we sort of have to figure out not only what parts we're using, but that requires us not just buying the parts and testing them to see if we're actually able to get them what we want to do. So, money genuinely is an issue for that, which you can divide that into two parts. The first one is getting money, which, we do rely on the university for that a lot, but you need to make sure that you have a good source and many sources, more than one source for your budget. Like, the university do provide a lot for us, but the thing is, they're not just they have other responsibilities. There are more students clubs than just us, so that means we're not they're not necessarily able to give us as much as they would like or we would like. And then, of course, the second problem is, how do you allocate the money you have? And again, with engineering projects this complex, you really have to be, clear on where is the money going and how can I and is it if it's going to things that aren't working out, you should really maybe ought to start cutting things. I mean, generally it's to put it in mathematical terms, it's a very complicated optimization problem, as everyone knows. Optimization is very hard indeed. And then our focus on accessibility does make that a great deal easier for us, because accessibility means that by the nature of the project we're doing, we do tend to spend less money than other people might. And the other problem and the other thing that helps quite a lot is our collegiality. We try to be very communicative about the things we're doing. That is, before any new piece of equipment is bought, we try to figure out, okay, well, precisely what problem this is trying to solve. Can we already use something else that's on the satellite to solve this? And if not, is there a better, more efficient, cheaper way we could do it too?
Cool.
Yeah, so again, communication, collegiality is key, no matter what.
Cool.
I'll just jump in and say something that really works for me, if that's okay. I've been on a lot of different engineering teams, and I think they've all had different feelings about the kind of subgroup nature and the almost hierarchical structure that we have, where everything is compartmentalized. I think on this team that has worked incredibly well, because there are so many parts of the satellite that definitely need to communicate with each other, but that also requires such domain-specific knowledge. And so I know over this past year, having our ADCS sub-team, which is a really small group of just 5 people, but us being able to work so closely with each other, get to know each other so well, trust each other so much, has been a huge help in our productivity. And having that kind of building very specific knowledge and then working across the organization to share and communicate that by having the things that we manage. And then finally, just sharing a vision and us all caring so deeply about our mission has made this an experience unlike any other, and really helped how much I enjoy working with the club, but also I see really pushed us forward and made us consider new things and take on new challenges that I don't think we would if we didn't all care about it so deeply or work so well together. So it's been a really amazing experience to see how the structure of the club has really facilitated that success.
Nice. I think that's a really, really nice point to end on. I guess a really good thing to say for our audience is where can people go to keep up with progress and see news of what's happening in the club?
Yeah, sure. We have a website up. It's called brownspace.io, and you can see our progress and our newsletters and our contacts up there. You can also email us directly at bsc@brown.edu.
Cool. Any final thoughts from anyone else? Doesn't look like it, but again, I want to say thank you to all of you for joining us for this ipXchange projects interview, and this has been so enlightening. I'm sure we could chat about this for indefinitely, because there's so many parts of the project that you can go into more detail on. But we'll be sure to put all those links when we do the write-up. And thank you for watching. Thank you for joining. And as always, keep designing.
Thank you.
Yeah, thanks for having us.
Thank you very much for having us.
Yep.
Hey, where my engineers at?